Hello everyone, so today we're going to be doing improper integrals. Boop. And so improper integrals is going to be the third, or technically the third video in this series, and the second topic we'll be covering. But improper integrals govern integrals that have one of two things within them. So either they have a bound that is infinity or negative infinity, right? Or they have some sort of hole inside of them. So, for example, 0 to 1, this is a very feasible number. These are two real integers. But if I put 1 over x in there, there's a hole on this interval. Or even if I did negative 1 to 1, there's a hole on this interval. Because if I do 1 over 0, because 0 is in the interval from negative 1 to 1, that would be a hole. So what you have is the 1 over x graph, it looks like this. And you have an asymptote. So when you have a hole or an asymptote in your integral, which we have here, then that's going to generate a big problem, because that means that you need to turn that into a limit as opposed to just a hardcore integral. Because if you did a hardcore integral, you're going to get the wrong answer here. Either you'll get the wrong answer or you get the right answer, but you'll still get marked down because you didn't show your steps. So that being said, this leads, why do we have these? Why do these exist? And I'm going to start with this example right here. Negative 1 to 1 of 1 over x. And this will probably be the only example of this that I go over, because it'll show you more or less what you have to do. So this is something that you're actually going to solve relatively normally, but you'll always want to check if you're going to have an asymptote or a hole, which is basically if I plug in some number, is it going to be 0? And this is always signified by x being in the denominator of a fraction, or x being inside of some sort of power. So for example, if I have x to the negative 1/2 power, that means I have 1 over the square root of x. So that means that I'm going to have that. Or even if I just have x to the 1/2 power, where I have a square root of x, this limits the amount of values you can have of x, because you can't plug in any negative numbers here. So that means that there's going to be some sort of limit on x. Same thing here. X has a limit imposed on it because you can't plug in any zeros in here. Or even if I had x minus 1, that means that you can't plug in 1. If I had, I don't know, x plus 2 squared, you couldn't plug in negative 2 here because that would give you a 0, right? So you just have to make sure that you find the restrictions that are placed on x. So that being said, what we're going to do is we're going to solve this. We're going to go ahead and solve this. So we know that for 1 over x, we know that there is a limit at 0. That at 0, we have an asymptote, so we have to establish a limit there. And how are we going to establish limits? Well, limits are going to tell us what our value would be, or what our value is projected to be. Think of it this way, right? If we have a stock market that's growing, right? We have a graph that says the stock market is continuing to grow. The amount of children we're selling on the internet is going up, and it's rising, and that's good for the economy, allegedly. So as it increases, we have this positive trend upwards, but people realize that selling children on the internet is bad, and they cut this off, and it crashes. Now, allegedly, this should have kept going up. If we see this trend that's existed, we know that this should be going up because trade is good. But some unforeseen circumstance, in this case, just the human enigma that selling children is wrong, this is going to plummet. The sales are going to go, boom, they're going to crash. And so we have this external element that's introduced that leads this line in a different direction than it's projected to. So in this case, this looks like it should keep going forever. These both look like they should keep on going forever. So our limit is going to tell us where it should be. But in reality, this just doesn't exist. That's the actual value. That's our whole graph crashing. So in actuality, it doesn't exist. But with a limit, we establish what it should look like. Based on the information that we have about the graph, what it should look like. And that looks like something that just goes on and on forever. And you can have shapes, or in this case, graphs, that go on forever and ever and ever. As a matter of fact, we have them as shapes. We call them fractals. These are things, I'm not sure if you've ever seen a snowflake drawn like this, where you have your snowflake, a very badly drawn snowflake, that has an infinite perimeter, but a defined area. Because on here, you'll have more small snowflake parts. And maybe on these snowflake parts, you'll have even more small snowflake parts. And it'll go on like that forever. And that has a definite area, but it has an infinite perimeter. So it's very interesting to see these things happen. So that being said, we have something that goes on forever, because this line here goes on forever. But this line also has a definite area. So you may find that even though you have to use these limits, we're going to use these limits because the integral might exist. We might have a definite area under that curve. And the only way to know that is by using limits, and that's why you want to incorporate them into the problem. If you didn't kind of understand that, just let me know, and you don't really need to explain that at all in the test. I just wanted to explain why we have to do this, because for most people it seems like a waste of time. So it may still seem like a waste of time, but what I'm going to do is split this at 0. So this means that we have two integrals, -1 to 1, -1 to 0 of 1 over x dx, sorry, I forgot the dx up there, I need to leave it off, plus integral from 0 to 1 of 1 over x dx. Perfect, awesome. Now what we can do is 0 is where we want our limits. We want our limits at 0. So what we can do is limit of, I'm going to call this a, as it approaches 0, of -1 to 0, of a, 1 over x dx, and then plus integral from b, plus limit as b progresses to 0, integral from b to 1 of 1 over x dx. And I'm going to make sure to define which direction these are coming from. Now, we have a plus sign when something is coming from the right, remember, because b is kind of coming this way, because our graph, the rest of our graph, is on the right-hand side. So when the rest of the graph is on our right-hand side, it is on the more positive end. It's getting more positive on the right-hand side. So that means this is going to be positive. And then for A is approaching from the left. It's coming from the more negative side of the graph. So that means that this is going to be a negative sign, right? Because these are not the same. These are not the same limit. This is going to give you something like negative infinity. This will give you infinity. We'll talk about that later. So that being said, what we'll do is we'll go ahead and see that you have integral from 1 to a of 1 over x dx, and limit is b to 1 of 1 over x dx. So I'm going to rewrite this up here now. I'm going to take the actual integral. And if you guys remember, integral of 1 over x from actually the last video is 1 over x is natural log of the absolute value of x. So what we have now is limit of a as a progresses to 0, negative sign, of natural log of the absolute value of x, and where x goes from -1 to a, and then b is going to be something similar. So I'm going to rewrite this really quick, where it's a and -1. So we have the limit as a progresses to 0 of natural log of absolute value of a minus natural log of absolute value of -1, which is just 1, because absolute value of a negative value is just the value of a positive, plus, and the same thing for b. So limit as b progresses to 0 of this stuff. In this case, we have 1 over 1. Sorry, we have natural log of 1, because we have 1 here, minus natural log of b. And now the -1 and the 1 cancel out, because you have negative natural log of 1 and positive natural log of 1. These two go away. And if you plug in the limit, if you evaluate the limit for a is progressing towards 0. So a will eventually become 0. And b will eventually become 0. And you said, and you probably are calling back to and saying, wait, I thought that limits weren't values. Limits aren't integers. And this is true. But what we're saying here is, instead of saying these two values are 0, we say that these two values are infinitely close to 0. And that sounds like they're the same thing. And that's because all math BS aside, they are very, very much the same thing. This is just what the College Board wants you to do, more or less. It has that weird mathematical explanation that's kind of cool, but still, they're basically more or less the same thing. So these two are basically 0. You plug them in, and they also cancel out, and they will actually give you a value of 0. Now, let's say you're doing a problem and you get a value that says something like this. You have an e of x and you get e of infinity in your problem. Then obviously that's not going to work out, and that's going to be, you're not going to want that in your problem. But let's say you get something that evaluates to e of infinity minus e of negative infinity. So long as the limits are more or less alike, they may or may not cancel out. Again, that depends on the problem. You might want to ignore that last bit because it's confusing, but overall, it's basically the same process, but just incorporate your limits because you'll get a lot of points there. So I hope that helped everyone in understanding why we do that. It's just solving things that are more or less the same, plugging in the variables and seeing where it takes you. So I hope that you guys enjoyed that, and let me know if you have any additional questions.